Have you ever, like, typed a prompt into an AI, corrected it when it got something wrong, and thought to yourself, I'm teaching it?
Oh, yeah. I mean, it's a very natural assumption to make.
Right, because we're so used to software doing that.
Exactly. We expect our apps to save our preferences and, adapt to our behavior over time.
Well, you aren't teaching it. In fact, you aren't changing its core brain at all.
Not even a little bit.
And that misconception is exactly why so many people fundamentally misunderstand what they're actually building.
The reality of what's happening under the hood when you correct a prompt is entirely different and honestly a lot more complex.
Welcome to No Hype AI, the deep dive that explains modern AI without unnecessary complexity or vendor hype. This deep dive explores just one of the ideas from the AI Builders Foundation, a practical, no-hype book about understanding AI and learning to build with it. Follow the link in the description to discover the complete book.
So our goal for you today is pretty simple. We want to strip away all the magic.
Yes, please.
We want to build a clear mechanical mental model of how AI actually works, how it learns, and why the biggest model on the market is definitely not automatically the best one for your specific use case.
Right, and to build that mental model, we have to start with the foundational question, which is, what actually is an AI model?
It's a great place to start.
Because I feel like the mainstream media often portrays it as this giant searchable database. Like, the assumption is you ask a question, and it scurries into a digital library to pull out a specific file folder with your answer written inside.
Yeah, which is completely wrong.
Completely.
If we really want to understand what a model is, a much better mental framework, especially for anyone with a development or engineering background, is an audio compression algorithm,
Okay.
like an MP3 file.
That is an interesting way to think about it, because an MP3 isn't the raw, original audio wave.
Not at all. When an engineer compresses, like a studio master recording into an MP3, they are stripping out vast amounts of raw acoustic data.
Just throwing it away.
Basically, yeah. The algorithm doesn't save every single sound wave. Instead, it captures the mathematical vibe, or I guess you could say the statistical patterns of the song.
Okay, so it figures out what frequencies matter most.
Exactly. It figures out what matters, discards the rest, and stores this highly compressed mathematical representation. So when you play that MP3, your software rebuilds a sound that is perceptually identical to your ear.
But, and this is the key, right? If you try to reverse the process and pull the original uncompressed, pristine studio master back out of that MP3,
You can't.
you can't do it. The precise, raw data points are gone forever.
They're gone. And that concept is the absolute core of what an AI model is. It is a compressed pattern system.
A compressed pattern system.
Right. So a massive language model has read, a significant chunk of the internet, but it does not store those raw websites on a hard drive.
It's not a library.
Exactly. It analyzes all that text to find the statistical relationships between words, concepts, coding structures, logical steps, all of it. And it compresses all those relationships into a computational mapping. Wow. So you give it an input, and it uses that compressed mapping to compute an output.
But that compression, I mean, that seems like a double-edged sword.
Oh, it absolutely is.
Because it's incredibly powerful, obviously. You can fit the synthesized knowledge of the internet onto a single server blade.
Mm-hmm.
But it's also a massive source of limitation.
Right.
Because you've compressed this broad pattern, you lose the precise detail. You can't just retrieve an untouched, pristine fact.
Which brings up the crucial question, right? How does it actually capture those statistical patterns in the first place?
Right.
To understand this, we have to recognize the two completely distinct phases in an AI's life cycle: training and inference.
Training and inference. Okay, let's dig into the mechanics here. If training is the phase where it locks in these patterns, what is actually happening under the hood?
Well, before training starts, our sources point out that a model is just an architecture.
Like an empty shell.
Exactly. It's an empty computational shell. Think of that empty shell like a gigantic, incredibly complex soundboard with billions of adjustable sliders.
Billions of them.
Billions. In machine learning, those sliders are called parameters. And before training, those sliders are set essentially at random.
So it knows nothing.
The model knows absolutely nothing. Training is this incredibly expensive, brute force process of adjusting those billions of sliders until the whole system can reliably predict the correct output for a given input.
But wait, how does it know which slider to move and by how much? Like, if I feed the untrained model a string of text about a database error and it predicts the next word should be, I don't know, banana instead of timeout.
Right.
How does the system correct itself?
It uses a mathematical process involving an error gradient. But let's simplify the math down to a smart thermostat.
Okay, I like that.
If you set your thermostat to 72 degrees, but the room temperature is 65 degrees, the system calculates the error. It's off by exactly 7 degrees.
Right.
It then sends a signal to the heater to increase its output to close that gap.
So it calculates both the direction and the magnitude of the required fix.
Yes, exactly. In AI training, the system feeds the model an input where the correct answer, which we call the label, is already known.
Aye.
The model makes a prediction using its current random slider settings.
So it guesses banana.
Right, it guesses banana.
Yeah.
The system compares the model's prediction of banana to the known label of timeout. It calculates a mathematical error score. Then, through a process called backpropagation, that error signal is sent backwards through the entire neural network.
Oh, wow. So it works in reverse. It's looking at every single slider that contributed to the wrong answer and nudging it a tiny bit in the opposite direction.
A microscopic nudge. And the system runs this loop to predict, compare, calculate the error, nudge the parameters billions of times across enormous data sets.
That sounds exhausting.
It takes a lot of compute. But eventually, the sliders settle into a configuration where the model consistently makes highly accurate predictions.
And that's it.
That final configuration of locked-in sliders is your trained model. Those parameters basically act as the model's long-term muscle memory.
Wait, okay, so if training is locking in the parameters, like that long-term muscle memory, what happens when I am chatting with ChatGPT on my phone?
Oh.
Is that a totally different process?
That is inference.
Yeah.
Inference is the everyday use of the trained model in a live environment.
Okay.
You hand it a brand new input, and the model runs that input through its locked-in soundboard of parameters to compute a useful output. The parameters themselves do not change during inference.
Which brings us all the way back to the opening hook.
Exactly.
When I tell a language model, no, you misunderstood my coding prompt, I meant Python, not Go, I feel like I am teaching it, but I am not adjusting its parameters at all.
Not even slightly.
But wait, it remembers my correction for the rest of the conversation.
Yeah.
How does it do that if I'm not changing its brain?
It does that through a mechanism called the context window.
Context window, right?
Yeah. If the parameters are the model's long-term muscle memory, the context window is its short-term working memory.
Okay, that makes sense.
During inference, everything you type and everything the model replies gets temporarily held in this context window. When you ask a follow-up question, the surrounding application feeds the entire conversation history back into the model as one giant new input.
Oh. So it isn't actually remembering me.
Yeah.
It's just reading the entire transcript of our chat over and over again, every single time I hit send, using its frozen parameters to analyze the whole block of text from scratch.
That is the perfect way to visualize it. And as soon as you close that chat session and the context window clears, that short-term memory is wiped completely.
It's not gone.
Gone. Unless the developer has built a separate database to save your chats and inject them into future context windows, the core model learned absolutely nothing from your interaction.
That fundamentally shifts how you have to think about interacting with these systems.
It really does.
But I want to rewind back to that training phase for a second.
Sure.
The model relies entirely on comparing its prediction to a correct label in the dataset to calculate that error gradient. Where do those labels come from?
They come from humans.
Ah.
Yeah. It is a very common trap for developers to treat data as a neutral, objective substance, like mining ore from the earth.
Right, like data is just data.
Exactly, but data sets are constructed artifacts. Humans decide what to scrape, what to exclude, and crucially, how to categorize the examples.
So historical data isn't objective reality.
Not at all.
It's just a digital mirror of whatever human behaviors produced it. Let's say you're training a model on a company's old customer service logs.
Okay.
And the human agents were chronically overworked, so they constantly miscategorized complex billing issues as simple password resets just to close the tickets faster.
Oh, yeah. The model will learn that exact inconsistency. It will look at the statistical patterns and deduce that complex billing issues should always be treated as password resets.
So it's perfectly preserving and automating human error.
Perfectly.
But you'd think the fix for bad data is just drowning it out with more data, right?
You'd think so.
Like, if OpenAI or Google just scrapes another billion websites, won't the sheer volume of good data eventually outweigh the bad human labeling?
That is the prevailing industry myth, but quantity does not cure problems of quality or relevance.
Really?
Yeah. 10 million completely messy, irrelevant examples are actively worse for a specialized task than 10,000 carefully curated, highly representative examples.
Wow, okay.
Massive volumes of poor data just dilute the useful patterns and introduce wild, unpredictable behaviors during inference.
If data quality is that treacherous, how do engineers prove the model actually learned the underlying concept rather than just memorizing the specific quirks and typos in the training set?
They do it by strictly quarantining their data into 3 separate buckets:
Okay, what are they?
training data, validation data, and test data.
So training data is what we just talked about, the examples used to actually calculate the error and adjust the billions of sliders.
Right. And validation data is a completely separate set. The engineers use this middle bucket to tune the overall training process,
Like why?
like deciding how drastically to nudge the sliders during backpropagation. But the critical one is the test data. This data is locked in a vault. The model never sees it during the training loop.
Never.
Never. It is only used at the very end to estimate real-world performance.
Because if you evaluate a model on the same data it used to train, it is basically an open book test.
Exactly.
It doesn't prove the model can generalize to a new problem, it just proves it memorized the answer key.
And generalization is the entire goal. You want the model to handle situations it has never encountered. But even with rigorous test data, you have to remember that a high score is conditional.
What do you mean?
It only proves the model performs well on that specific distribution of data. If the real world shifts, like if user behavior changes or a new software framework is released, the model's accuracy can fall off a cliff.
Because the live inputs no longer match the statistical patterns it learned during training. Okay, so we've trained the model on this curated data, locked the parameters, and we handed a completely novel input during inference. It hasn't memorized the answer. It has to compute one. How does it do that if it isn't actually thinking?
It calculates probabilities.
Probabilities, yeah.
Let's say you built a classification model to detect network anomalies. You feed it a new server log. Internally, it doesn't just decide this is a threat.
Right.
It computes a mathematical score for every possible category. It might calculate that the log represents a DDoS attack with 70% probability, a hardware failure at 20%, and a routine traffic spike at 10%.
So it deals entirely in likelihoods, not absolute certainties.
Always. And this highlights a critical architectural concept. The model's output is just a raw probability score. The surrounding software system determines what that score means for the business. A probability is not a decision. The engineering team has to write deterministic code that says, if the DDoS probability is above 80%, automatically trigger the firewall rules. If it is between 50 and 80%, page the on-call engineer.
That makes perfect sense for a classification task where you just get a percentage. But what about generative AI?
That's where things get tricky.
Yeah, because when I ask a language model to write an email or explain a piece of code, it doesn't give me a dashboard of probabilities. It gives me beautifully formatted, incredibly confident paragraphs.
And that's why generative models are dangerous. They hide their probabilistic nature behind a seamless interface.
They seem so sure of themselves.
But a language model is fundamentally doing the same thing. It is calculating the probability of the next single token or piece of a word.
Just the next word.
Just the next piece of a word, yeah. It picks one, injects it into the context window, and then calculates the probabilities for the next token based on that newly updated text. And it does this over and over incredibly fast.
Here's where it gets really interesting for you listening. It is exactly like a charismatic actor delivering a line on a stage.
Oh, I like that.
Right. They can sound completely convincing, projecting total authority and expertise, even if they completely forgot the actual script and are just improvising words that sound dramatically appropriate.
That is a brilliant way to frame it. Confidence of tone is not a calibrated measure of correctness.
Right.
These models learn the style of authoritative writing from their training data. Textbooks, research papers, confidently written articles.
So they just mimic the tone.
Exactly. They apply that confident style universally, whether they are retrieving a known fact or stringing together a statistically likely but entirely fictional sequence of words.
Which brings us to the elephant in the room. If confidence does not equal correctness, how do you make sure you are using the right model so you aren't just generating confident nonsense?
It's the million-dollar question.
Because the vendor hype is deafening right now. The sales pitch is basically, just buy access to our massive trillion-parameter foundation model, and it will magically solve all your engineering problems.
Yeah, and our sources are adamant that this bigger is always better mindset is a trap.
A trap. Okay, why?
To understand why, we need to separate the concept of a foundation model from the concept of adaptation.
Okay, if specialized models are cheaper and safer, why is every tech giant burning billions of dollars and megawatts of power to build these massive, generalist foundation models in the first place?
Because training a highly capable model entirely from scratch is prohibitively expensive for most companies. The foundation model approach solves this. A tech giant spends the millions of dollars to pre-train a massive model on a vast dataset, essentially scraping the internet.
Right, the brute force part.
Exactly.
Yeah.
This creates a foundation with a deep, general grasp of language, logic, and coding structures.
Pre-training gives you a very capable generalist, but you don't necessarily want a generalist for a specific production task.
No, you adapt it, and there are several ways to do this. You can use fine-tuning. This is an additional round of training. You take that pre-trained model, and you run backpropagation on a much smaller, highly specialized data set.
Okay.
You are mathematically shifting the parameter weights so the model adopts a specific tone or learns a very specific proprietary coding language.
So fine-tuning actually changes the long-term muscle memory.
It does.
What about RAG? We hear about retrieval augmented generation everywhere in cloud-native development.
Yeah.
How does that adapt a model?
Well, our RAG is an adaptation at inference time. It doesn't change the parameters at all.
Oh, okay, so it's different from fine-tuning.
Very different. Remember the context window, the short-term memory?
Yeah.
With ARG, when a user asks a question, your surrounding system first queries an external database, retrieves relevant factual documents, and physically pastes that text into the model's context window alongside the user's prompt.
Yeah. Ah. So instead of relying on the lossy compressed parameters to remember a fact from 3 years ago, you are handing it an open book and saying, read this specific document right now and summarize it.
Yes. You are anchoring its statistical generation to retrieved facts. And you can also give the model access to tools.
Like what kind of tools?
Like, if the system detects the user wants to calculate a complex architectural load, instead of letting the language model guess the math, the system connects it to a Python interpreter or a calculator API to generate the exact number.
This completely undercuts the idea that you need a massive model for everything.
Completely.
If you can fine-tune a model or anchor it with a RAG, why bother with a trillion-parameter behemoth?
Well, model size is often treated as a proxy for intelligence, but size introduces massive operational trade-offs.
Right, like cost.
Cost is a big one.
Yeah.
A larger model has massive latency. It takes longer to compute every single token. It requires specialized GPU hardware that costs a fortune to rent, and it consumes vast amounts of electricity.
Not to mention data privacy. If you're a healthcare company or a financial institution, sending highly sensitive, unencrypted user data via API to a cloud provider's massive model is a massive compliance risk.
Oh, huge risk. A massive general-purpose model is like a Swiss Army knife. It can do a bit of everything. But a specialized, smaller model is a scalpel.
Right.
If your system's only job is to analyze log files for security breaches, a small, heavily fine-tuned model running locally on your own infrastructure will be faster, vastly cheaper, entirely private, and likely more accurate than a generalized cloud model.
But even if you do everything right, you pick a fast, specialized model, you set up OG, you curate your data, the system can still produce completely incorrect outputs.
It happens all the time.
And when that happens, the industry's favorite buzzword is hallucination. But I feel like our sources treat that word as a cop-out.
It is a dangerously lazy diagnosis. Slapping the label hallucination on an error obscures the mechanical root cause. A model failing isn't one magical phenomenon. It is an engineering failure, and different causes demand completely different architectural fixes.
Let's break down the actual failure modes. What is usually going wrong when a model seemingly loses its mind?
The most common failure is simply an unclear task. If a user inputs a vague prompt, the model has to guess the intent. It generates a statistically plausible response that misses what the user actually wanted.
So how do you fix that?
The fix there isn't a better AI. It is better UI designed to constrain and guide the user's input.
Or it could be an input mismatch, right?
Yeah.
Like you trained a specialized vision model exclusively on pristine, high-resolution architectural blueprints.
Sure.
But in the real world, engineers are uploading blurry, badly lit photos of blueprints taken on their phones.
Exactly. The statistical patterns of a blurry photo are completely different from a pristine scan. The model will fail catastrophically because the live data doesn't match the training distribution. But, the most destructive failure mode has nothing to do with the model's parameters and everything to do with human overtrust.
I want to dig into this. What does overtrust actually look like in a deployed application?
Let's look at a real-world catastrophe. We have seen high-profile cases where lawyers used generative AI to prepare court filings.
Oh, I heard about this.
Yeah, it was bad. The lawyers asked the AI to find legal precedents. The language model, lacking a RAG-E system connected to a real law library, simply calculated statistically likely strings of legal-sounding text.
So it just guessed.
It completely fabricated case names, citations, and rulings, and the lawyers trusted the confident tone, didn't verify the output, and submitted fake cases to a federal judge.
Wow. Because they treated a probabilistic pattern matching engine like a deterministic search engine, they assumed it was retrieving a file, not improvising a script.
Exactly. The failure wasn't the AI generating text. That is what it's designed to do. The failure was the surrounding system and the human operators assuming a 100% accuracy rate for a high-stakes domain without human escalation thresholds.
Right.
Even if a model is 99.9% accurate, if you deploy it to process 10 million automated financial transactions a day, you are guaranteeing 10,000 unhandled errors will slip into your production systems.
What does this all mean for you listening? It means if I build a system that asks a language model to calculate complex tax liabilities, and it makes up a number that gets my user audited, the AI didn't hallucinate. I just fundamentally failed as an architect.
You did.
I used a pattern matching tool when I should have used a calculator.
You have to map the tool to the task. Exact calculations, live database lookups, and authorized system actions should never be improvised through probabilistic generation. If you need a verifiable fact or a hard rule, you build deterministic software.
This conversation strips away so much of the vendor mystique. To recap the mental model for everyone listening, AI operates in two distinct phases. Training is the expensive, brute force process of using curated examples and backpropagation to adjust billions of internal parameters, the long-term muscle memory.
And inference is what happens in production. You feed new inputs into that locked-in parameter state to compute a probabilistic output, using the context window as a short-term workspace. By understanding this, you stop treating AI as magic and start treating it as an engineering component with clear constraints.
We learned today that an AI's confidence is just a learned stylistic pattern, completely separate from its actual factual correctness. It makes you wonder, how much of human confidence in corporate meetings is exactly the same thing?
Oh, wow.
Right. Just an improvised string of buzzwords delivered with absolute certainty without a shredded data to back it up.
That is a slightly terrifying but highly accurate thought to leave on.
If this deep dive helped you understand AI more clearly, follow No Hype AI on your podcast platform or subscribe to @RepulsedPaddle on YouTube for more practical content about Go, cloud-native engineering, and AI native development. This conversation was produced using NotebookLM's AI-generated hosts and is based on the book The AI Builders Foundation. You'll find the book and author details in the description.